and trying to figure out what the reference level is. If you're going to use conservation of energy, I just put an extra green line here to kind of indicate, well, that's where the center of mass is going to be when the object swings downwards. So this is likely the height. Well, we have a value to use for that. That's the radius. But in any problem where you believe you're going to be able to do conservation of energy, you need to identify what is your height for your problem. What is the lowest point that the center of mass can make it to? Our objects have extension now. So it's not enough to say what's the lowest point it can go to. We have to add a little bit more than that. Now, I think in this case, the amount of gravitational potential energy is going to be just mgr, right? Because we have lifted the center of mass 1 radius high. Now, when it makes it to the bottom, there is a fixed pivot point. That means that the only kind of kinetic energy we can have at the bottom is going to be rotational kinetic energy, 1/2 I omega squared. And this object is a disk. And so I saw a lot of you using the moment of inertia of a disk in your work. That's great. It is a disk. But this is the moment of inertia of a disk spun about its center. But we're not spinning it about its center, so you're going to have to do some work to figure out what the actual moment of inertia is. And we talked about this too, that we'll have to shift the moment of inertia from the center to a point on the edge, which means using the parallel axis theorem. Had the right idea. It's subtle, I know, it's small, but this is what you actually have to do. Maybe try doing that and see if that fixes your mistake. By the way, the shift distance is 1 radius. All right, we're shifting it from the middle to a point on the edge. That's a shift of 1 radius. So I'm pretty sure this gives us 3/2 mr squared. Now you just got to bring all those pieces together. mgr, the amount of gravitational potential energy, 1/2 I, which is 3/2 mr squared, times omega squared. Now, doing the algebra is not much, there's not a whole lot of work there. You're just going to solve this for omega. I'd probably cancel out one of the m's, and maybe cancel out one of the r's. And 1/2 times 3/2 is 3/4. So this gives you the square root of 4g over 3r. Still not the answer. Do you know why that's not the answer? That's right, I asked for the velocity of the center of mass. This is the angular speed of the whole disk. So the whole disk has this angular speed. But I wanted the velocity of the center of mass. So yet one more step, because you have to give the answer that you're asked for, not the one you want to give. So that's got to be V equals omega times r. And I'm using little r here to remind you that this is how far away from the pivot point the velocity is that you're looking for. So we're looking for the velocity here, right there. So that suggests we're going to need to shift from the pivot a distance, big R. So V equals square root I just squared it and put it inside the radical. That's how I got v equals the square root of 4/3 GR. It's a long way from a block slides down a ramp. A long way. Yeah.
Have we left it at v equals square root 4g times r? Like, would that still calculate?
I mean, they are numerically the same, but I think I could expect a little more from you. But I don't know that if you did all of this, if you'd lose any points. Yeah.
So you put it inside the radical by square rooting it and then
No, you square it to put inside the radical. Does that make sense? I mean, how many of you have done this before?
never done it before.
Okay. If I want to put something inside the radical, then remember the radical represents everything inside is to the 1/2 power. I'm going to write r as r squared to the 1/2 power. Fine. That's still just r, right? So I have it squared, but I have it inside. Now, because I have these two parentheses r to the same exponent, I can combine the two parentheses together, and I'll get 4g over 3r times r squared to the 1/2 power. And now, of course, I have an r squared in the numerator and r in the denominator, so this reduces down to 4gr over 3 to the 1/2 power, which I just wrote as 4/3, but you could take the 4 out of the radical if you want and take the square root of that because it is a perfect square, and you could have, 2 gr over 3 to the 1/2 power. That's all okay. And these are all equivalent, but is preferred rather than this one. Is we've done a lot of stuff where we've just dropped something, right? If I just drop something from here and it falls a distance h, and I ask how fast it's going right before it hits the ground, do you remember what that is? I mean, I've kind of recommended that you memorize it, but I'm often surprised that you don't. That's just square root 2gh. So we have something similar here, but the fact that it has more inertia because of the way it's rolling, we still get this g times the distance here, just like we have a g times the distance here. So part of the reason why cleaning it up is nice is it gives you some reassurance that you're in the right form of the answer. It also helps with things like, this is meters per second squared times meters. I'm just looking at the units of g and the units of r and trying to know if at the end of all of this, very, time-consuming algebra, do I have anything that remotely resembles what could be the right answer? Well, I'm looking for a velocity. So inside there, I've got something that's in terms of meters squared per second squared under the radical. So that suggests that this would actually be meters per second. That's suggestive that I'm going to get the right answer, that I have my algebra correct. So those are just little things as to why. Now, this kind of problem is just an exercise. There's a lot of pieces here and a lot of ways to get tripped up, but this is like multiple choice kind of stuff. A direct idea that leads to an answer. On our AP exam and on your next test, you know that being able to explain things becomes more important. So one thing that I would want you to be able to do is be able to take a look at the system we just saw and then be given a system that's similar. So a disk and a ring that have the same, say, radius and the same mass. And I attach both of them to a pivot point about their edge. Without doing any math, which one of these will swing down with the largest velocity? The disk or the ring? Now, what I want you to do is I want you to, in your notes, write that question. This is a sample. This is the kind of thing that'll be on your test. And you've seen that in your homework. I've given you quite a bit of questions like this, I hope. I hope you've seen your homework. Maybe started it. So if this were your question, which one of these two objects will swing down with the largest velocity? They both have the same amount of starting energy, which would be a good thing to start off with saying in your explanation. If you were asked to explain without math which one of these two objects would be traveling fastest at the bottom, what would your sentences look like? Try it. I think there's 3 or 4 things you have to say. Would somebody be willing to read theirs? No courage? Wow. It's hard to find bravery, I guess. So I have to pick on one of you? I can do it. No one's even going to look up. All right, so how many agree with that statement? You had courage, you read it. I think that statement alone would get you most of the points. There's a few things missing from it I think that you should state. But I think what he said, by making it clear why he knew one of them had more inertia than the other, he said, he explained why he believed the disc had less inertia than the ring, and he explained that because one of them had less inertia, it would be easier to turn. I think those two things are clear and they're concise, and they explain to a person who's reading it that not only does he know the word moment of inertia, but understands the implication of moment of inertia. I think there's a couple other things that probably should be brought up, that even though we're not spinning it about its center, the disc still has a larger moment of inertia. I think you have to indicate that you understand that you have to shift the moment of inertia for that. And I think that's a good thing to bring up. I think it also, if you want to make sure you nail it, you indicate that both objects start with the same amount of energy and end with the same amount of energy. But because one of them has more inertia, more of that energy is used to spin the object up, and therefore it's not going as fast. But I think referencing the energy is important here. But I think if it was a 4-point response for that paragraph, I think that was probably 3 out of 4 points. So, good job. I want to move away from these things where the object is fixed in place, and I want to talk about something else. I want to talk about rolling. We know the answer to this because we did this in class. But I want to talk to you about how we deal with problems in which an object is going to be rolling. Let's handle the fact that there are possibilities for what happens here. If I put something like this, a ring at the top of a ramp, and I release it, there's actually more than one thing that could happen. And you need to be aware of all of them. First, this could be a slippery ramp. Maybe it's icy or something with a very low coefficient, or a coefficient that's almost 0. If that would be the case, this object won't roll. It'll slide. It'd just be like a block sliding down a ramp. So one possibility is that your object could slide down the ramp. Rolling isn't a given. So sliding without friction is a possible outcome, and you need to be careful when you read your problems. If there's no friction, then there's nothing to cause an object to spin or turn if it's supposed to roll. Rolling is a process that involves a little bit of friction, and that friction causes the object to spin while it's moving. So if you have no friction, there will be no change to the angular speed. So the change in angular speed will be 0. I'm being very careful about how I present this, because I want you to know if the object is already spinning and you put it on a slick surface, it stays spinning. That's going to be important because I'm going to try and trick you. So if your surface has no friction or very low friction, then there'll be no change to the angular energy. That also means no change to the rotational kinetic energy. That energy stays the same. Without friction, this object behaves as the block would behave, just slides. So then there's this process called slipping, or sliding with friction. This is where the friction is not zero, so it's not perfectly slippery. But these things aren't linked up, meaning the rate that it spins isn't related to how fast its velocity is going. So it can have a velocity and an angular velocity, and they may not be the same. The total energy will still be the sum of the translational kinetic and the rotational kinetic, but they're not connected together. However, the friction will cause changes to the angular speed. Friction will cause changes to the angular speed. Rolling is specific. If you are told that something rolls, you're being given a very specific piece of information. First, this has to be true for the condition of rolling. There is a link between how fast the object's moving and how fast the object is spinning. They are directly connected together. Also, rolling takes place with static friction, not kinetic. Slipping or sliding with friction takes place with kinetic friction. But when an object is rolling, this point of contact does not slide. It's at rest. An object that's rolling, the point that touches the surface right here is at rest, just for a moment, but it's at rest. It's not sliding. That is the condition for rolling. So if you're told something is rolling, you're being told to use this. Now, I'd like you to try this. I'd like you to try it out. I want you to see how this works. It's not a whole lot, but let's just say that I have a ramp, and I'm going to give you numbers, although I would encourage you to work this out algebraically and plug the numbers in at the end. Let's say you have a ring, and it is 1 meter above the baseline, and it's going to roll down the ramp from rest. So up here, it's at rest. You release it. By the time it makes it down here, it's got some linear velocity and some angular velocity. Now, I'd like you to tell me how fast it's going at the bottom. Let's say that it is a 15 centimeter ring and has a mass of 250 grams. I want to know how fast it's going at the bottom. Now, if it was sliding without friction, it would be going one speed, but we're talking about friction here, so we're talking about rolling. I want you to work this out. Now, this is a clear conservation of energy question. Do you see why it's a clear conservation of energy question? Do you see a change in the height of the center of mass? Yeah. Conservation of energy, pretty clear. Center of mass is going to change a height of 1 meter. At the bottom, though, it's going to have two kinds of energy, translational kinetic and rotational kinetic. At the top, it has no kinetic energy because it's not moving, so all the energy is gravitational. So in this problem, we're going to set the gravitational potential energy equal to the kinetic energies at the bottom. But there are two kinetic energies now, rotational and translational. So mgh at the top is going to equal 1/2 mv squared plus 1/2 I omega squared at the bottom. Now, we are told this object is rolling, but we still have to deal with the fact that it has a moment of inertia. So you will need the moment of inertia of this shape. And since it is rolling, it is spinning about its center. So all you'll need is the moment of inertia about the center of mass. So you got it on your chart, right? A ring about its center, what do you got? Just mr squared, that's right. So first things first, in all these problems, you're still going to be dealing with rotational inertia. So I'm going to plug in my moment of inertia first. Now, here's the important thing. We want to know how fast it's going. We're looking for V. Well, V shows up there, but clearly it's related to how fast it spins too. So in a problem where these two things are connected, you want to put these two things together. And something special happens when you try to do that. To put them together, I'm going to substitute in, and this is the most important step. When you know something is rolling, you get to use this. And this is where it gets used. We put everything in terms of the type of velocity we're being asked about. In this case, we're being asked about the linear speed of the object that's rolling. So I'm putting everything in terms of the linear velocity. Now, if you look carefully, the r's cancel out. I have 1/2 mv squared here. I have 1/2 mr squared times v squared over r squared. In rolling problems, this is really common, especially for an object that rolls like this, about its edge. These two r's disappear, and I'm left with 1/2 mv squared plus 1/2 mv squared equals mgh. Now, just a brief aside for you guys because you're going to have to start making connections here. If it was back in November when we were first introducing this and it was just a block sliding down a ramp, do you remember that? We would have had mgh equals 1/2 mv squared if there was no friction. Now you'll notice this one doesn't have the 1/2 here, right? Because we added the moment of inertia and we have two forms of energy. So the energy is being split up into two places. This is why an object rolling is often going to be slower than an object that slides without friction. Because the energy gets divided up into one part translational and one part rotational. How much it gets divided depends on the shape of the object. Objects that are harder to turn will divide it up more and give more of that energy to the rotational side. Objects that are easier to turn give less of that energy to the rotational side. But some of that energy gets siphoned off. Now, oftentimes, when things slide, they have to contend with friction, so there might be some work done by friction that gets lost for an object that slides. But I'm trying to make sure you understand that rolling isn't going to be as fast as sliding without friction because energy is getting divided up in a way that wasn't being divided before. Now, also, did you notice that I wanted to do this without having any variables in? Without putting any numbers in because many of the variables that you were given ended up not being a part of the answer? This way, if you do it algebraically and you're not given a value, you don't say at the beginning of the problem, well, you didn't give me the mass, so I can't do it. Are you sure you needed it? So V equals square root of GH. So about 3.3 meters per second. Right, square root of 10. Height was 1 meter. G is 10. Can you repeat this real quick for a disk and prove the disk gets down there faster? Not a whole lot different to do, right? You're just changing one thing. Instead of mr squared, it's going to be what? 1/2 mr squared. That's right. That's the only difference. So I get 4/3 GH, which doesn't seem like much, but that gave me 3.65 meters per second at the bottom, towards the actual square root of 10, which is 3.16. Is that much different? It's different. Sure. Easier to turn a disc than it is to turn a ring, so it makes it to the bottom faster.